Morning, everyone. So I realize it's 9 o'clock in the morning, so we're still waiting for a couple of people to join. So my name is Fawaz Ghali. I am the developer advocate at Hazelcast. My goal for this session today is to go through some kind of real-life use cases where we can discuss and share a few ideas about real-time stream processing. And particularly, we're going to discuss fraud detection. So I think it's pretty much anyone is involved in some kind of fraud detection, whether it's like personal or at work. So this talk, essentially what you can take out of it is what kind of challenges exist for fraud detection and what kind of solutions that we can use in order to either prevent or avoid. So before we actually get going with the subject, what I would like to discuss is the concept of real-time. Real-time means different things for different people, so it will not be the same for everyone. So if I now ask everyone in this room, what do you think about real-time? Some of you might think in terms of maybe minutes. Others might think about days or hours or weeks. So it varies, but essentially what we're discussing real-time for fraud detection is pretty fast. So for example, if we think about blink of eye, how long you think it takes for an eye to blink, roughly? So on average, it takes like 1/3 of a second. So that's pretty fast. If we want to discuss, for example, clap of hands, it's 1/7 of a second. And for example, the camera flash takes like 1 millisecond. So as you can see, these type of activities are quite fast. And essentially, it's hard for a human eye or even normal software development to handle these type of requests. So you might think, okay, maybe not all applications require some kind of real-time stream processing, but essentially it's everywhere. Wherever you go, wherever you discuss, whether you're using your mobile phone or using your laptop or you're using any type of, IoT devices, you kind of like using some type of real-time stream processing. So for example, here you can see financial institutions, some example here. We have like internet applications, we have hospitals, we have like sports, and we have machine learning. So it's kind of like everywhere. The examples of real-time applications essentially unlimited. But for the sake of this talk, what I want you to focus on is the financial institutions, how they handle fraud detections, and how you can also use it for your advantages as well. So most of us work in type of high performance. So if we want to discuss fraud detection, essentially we need to discuss two concepts here. So we have to discuss the high performance payment processing and robust fraud detection. So majority of solutions either focus on the first part or second part of this equation, and essentially what you want is to have combination between both. So the combination between both allows you to have more success when it comes to handling fraud detection. Obviously, how many transactions per second is like an important factor. Remember, we're talking about sub-milliseconds. So we're not talking about like a few hundred of transactions. We're talking about 20,000 on average per second. So if you really want to handle fraud detection, you want to develop an application where you can process so many transactions per second. The benefit of using this type of technology is like you can save money basically. So for example, I will show you a real use case where basically a company managed to save around 100 million, or even you can have some kind of improvement in performance. So whether it's like running 4 times faster or even 20 times faster between 2 months and 2 days. So as you can see, there is like really huge gap between these two edges of this story. And it's not only how you develop your application for real time, but also how you can scale it, right? Because what it works on one machine or one cluster doesn't mean you can expand it or you can scale it. So I will show you some examples here how you can scale it. But before we proceed to this, I would like to highlight what kind of use cases we can focus on here. So for example, fraud detection has multiple elements included in it. So for example, duplicated testing, where we can test same transaction, whether it's like two transactions share some kind of or overlap, whether it's at a time or location, or maybe a combination between multiple factors. Or pattern detection. So for most of us, like for example, I don't know, like at the start of the month, our bank accounts might be high, and then it starts to decline, and essentially it goes really down or to the bottom on the end of the month. So this pattern can be also detected. Also, we have some kind of account scoring. So whether we have multiple accounts, we can give multiple scores to handle fraud detection. And identity theft, for example, another example of fraud detection, and the false positive. For fraud detection, false positive means essentially you're declining valid transaction, and this costs money, right? Because after all, businesses make money from transactions, so you don't want to decline a valid transaction. So you also want to reduce this false positive. Now, if you want to, start thinking about the architecture, what we can do, if you look at this diagram here, there is a good part of it and not so good part, unfortunately. So the transaction, you see it here, most of the time, actually we can't do anything about it, right? Because it requires some kind of hardware, network hoops, and so on. And no matter what, you still have some kind of latency on this. So you have very small or even very tiny window where you can apply your fraud detection solution. And this is essentially, we're talking about sub-milliseconds. And if we want to dive in how we can implement this, essentially we go for the time-based SLA, where we have from one side, if you think about using your credit card or debit card, you swipe it, right? And this swipe goes to your card provider, and you kind of like do some kind of validation and checking back account balance and so on, and you respond in this. So the time it goes and comes back, this is unfortunately you can't do much about it because it requires some kind of network infrastructure, hardware, input, output, read and write processing. So what you can do is you can exploit this very little tiny window here where you can apply your solution. And even this, you might think about it as one direction solution. So it goes to your card provider and comes back. Unfortunately, it's not as simple. So if we also want to dive in and look at the solution, for example, here, it might be easier just to look at the coloring here. So you have the Viridian color, which is the authorization, for example. You have a response in orange, and you have the purple, which is like the cleaning. So you can see here, the moment you start, for example, swiping your card, it goes to the merchant, and this will go to your payment processing gateway, and this will be connected to the credit card network, which goes to the issuing bank, and it goes back again for the response, and then with the clearing. So usually these two steps happen at the same time, but not necessarily. So it depends on where you apply it to. And again, just to add some complexity for what we were going to discuss today. So we discussed the process of it, but at the same time, it's not one card, right? So you might be doing some kind, I don't know. For example, core banking, physical banks, or you might be looking for, internet payments, or, ATM or mobile, or a combination between all of these, right? So this is where the channels comes from one side. And also we have another part of this story, which is like the payment networks, which cover also multiple channels as well. So we have, for example, business to business in some cases, or foreign exchange, for example. I come from the UK, so here I need, for example, to do some kind of, money exchange. So this is also involved in the fraud detection. And your solution in the middle consists of two blocks, right? So we have the payment hub. So this will require some kind of authentication for the card, for example, or account. The fraud detection solution and network selection. So this is based on geographical location. And we also have the operational data store. The operational data store doesn't mean like traditional databases. It means like some kind of caching solutions, right? Because most of the time when you deal with fraud detection, you want to have the process as fast as you can. And one way to do it is to cache as much information as you can about specific account, or specific details for your solution, and you store it in some kind of operation data store. So this operation data store allows you to faster access to whatever you store in your database. And we also have the gateway, so which is also still part of the payment hub, but it's not related to fraud detection. As I mentioned, I work for Hazelcast. So some of you heard of Hazelcast. So the platform essentially is a real-time stream processing as well as a caching solution. It used to be two components. But now it's one platform. It's open source, so you can try it out. Everything I talk about today is open source, even my demos. So feel free to try it out, give it a go. And essentially, what you want is to handle your sources, right? So if you remember from previous slide where I mentioned, channels, you can look at it in here. So this is kind of like, for example, you might have transactions, messages in Kafka topic, for example, or it could come from IoT, for example, GPS coordinates on mobile devices, or it can come also from enterprise applications. So if you have Open Bank, for example, or even like in most cases, a combination of multiple sources, right? Because after all, it's not only one source who determine if there is a fraud in a payment process or not. So once you have your source, you can feed it into the platform. The platform itself has some kind of, like I mentioned, two main components. So we have the fast data or the caching solution. So this deals directly with your external data sources. So think about it as, I don't know, JSON files, XML files, physical databases, and so on. And you load it into memory first of all. And as you get real-time transactions, that's where you can do some kind of fraud detection. Remember, a real-time stream processing, if you want really to do it right, you need both elements. So you need real-time transactions as well as some kind of batch mode or batch data, for example, account details or location details and so on. Real-time stream processing in general, never about real-time transactions. It's always about combination between the two. And Hazelcast provide this for you, so you can load whatever you have in your batch or your data stores into memory, and you can also have the processing on it. So for example, you can do some kind of transformation if you want to do it, or even you can aggregate multiple sources, or even do some kind of stream processing, or do some kind of machine learning as well. Now, I realize that's not all of us use Java, so the platform itself is built on top of Java virtual machine, but we have multiple clients for it, so that's where the flexibility comes into place, because if you work with microservices, you probably know that not all microservices are written in the same language. So if you have, like, for example, I don't know, one microservice in Java and the other in C#, and you want to do combination, so this is the platform itself can allow you to do so. And we have also SQL as well on top of it, which means that you can do, I will show you today how you can do it. So essentially, you can do some kind of stream processing within the SQL itself. Obviously, once you're done with this, you can output it. So you can send it back again to Kafka, for example, or you can send it to messaging queue, or even like, if, for example, if you want to do some kind of alerts for detections, if it happens, of course, you want instant alerts, right? So I'm not interested, for example, is if my card is being used somewhere else yesterday, right? Because that doesn't give me, I want alert now if something goes wrong. So obviously, because it's open source, which means you can write your own source. So if the source doesn't exist, for example, you can write your own, and same thing for the sync as well. So the platform is quite flexible. And for the fraud detection, as I mentioned, there's two elements in it. So you get your transactions here, for example, coming, for example, in Kafka topic, or as I mentioned, the GBS coordinates or combination between two, and you take it into the platform itself, where you can use some kind of machine learning on top of it. Some of you prefer to use Python for it, and others prefer to use some kind of different C++. And this is where you can connect also your microservices. Now, the important part when it comes to fraud detection is not to handle it in one way. You want to actually be able to scale it, right? So the scaling mechanism is essentially, we have some kind of auto-scaling feature which allows you to either scale up or scale down depending on transactions you receive, for example. So for example, if you're handling online transactions on websites, you know, for example, maybe you get spikes on towards the first of the month or Black Friday, or even around Christmas time. So you want to be able to scale it. And what is nice about this type of scaling is you can do scaling both on compute, so on the stream processing, as well as your data. So it allows you essentially to distribute your load, whether it's a processing or even your data, and this gives you some kind of flexibility. So it allows you to do it on the exact node. So which means you save more time in terms of the latency. And when it comes to write the actual algorithm here, so what I want just to highlight is this complex solution requires some kind of interaction between multiple services, or multiple, I don't know what you want to call it, but essentially multiple scripts. And here you can see you can basically mix and match between your input and processing as well as output. For example, the first ingest you can direct it to is, second machine learning score, and vice versa, and you can deliver it also to multiple outputs. So the platform itself allows you to do so, and most of us is stuck at the top of it. So for example, if you want to, write a solution, usually you want to write multiple solutions, right? Because after all, whatever you collect and do for your algorithm, is just give you one score. So what is needed for fraud detection is to combine multiple scores in real time, because these change over time. So whatever is valid now for fraud detection might not be valid for tomorrow or next week. That's why you want to have multiple algorithms in place, and you kind of like look for composite score. So you take one algorithm off, for example, and the platform will allow you to actually combine between multiple algorithms in order to do it. Now, you might be wondering what type of data here exists and what type of performance it requires. So I mentioned 20,000 transactions per second, but that's just part of the story, right? Because it's not about, one individual, entity, one individual person or bank. It's like combination between multiple users and multiple banks. And we've done some kind of gigascale experiment where we really try to scale the application. And what we managed to do is 1 billion transactions with under just 30 milliseconds latency, and that was on 45 nodes. So think about it. What is good about it is the linear scale. So whenever you have more transactions, essentially you can expand it. And 1 billion transactions is really big number, but obviously that's just like a first step of this process. So some of you might heard, for example, of Flink or Spark to do it, and the lower on this graph, it shows you the lower latency. So you want to make sure whatever you can save on time for processing or compute and your data is to use it to your advantage. And now the scaling itself, as you can see, so we have different parallelism, depends on how many nodes you have and how many basically events you can handle per second. So if we look at like one node cluster, as you can see it here, so we have transactions and we have the Skylern machine learning algorithm, and we can see difference. If it is just basic REST, you can handle, for example, 5. If you expand it to use the same processing without parallelism, you can get up to 20K. And if you can use on 4 cores, for example, you can get it up to 100K. So you want to make sure that you use it to your advantage when it comes to scaling your application. Now, I will show you a real use case. Then we proceed to the demo. So I have 2 demos for you today. But let me just go through the use case first. So essentially, we have like a fraud detection use case. That's a real bank here. And you can see, if you look at that on the other side of the screen, you can see the yellow part is the lost fees in terms of how fraud detection works. So this is jumped from, for example, or reduced from 9 million to actually 7.4. And the fraud detection loss, for example, in the orange, you can see it roughly around 1,000. And this has been reduced in terms of the using the scaling for fraud detection. And essentially, you end up saving around 1 million, and this is per year. So let's jump quickly for the demo. So what I will show you for the demo is, first of all, I have 2 demos. So the first demo is a real use case where any one of us has or encountered this process here. So think about it if you're in 2 places, right? So for example, if you're in London, for example, this is where you have, for example, 2 hours time window between London and Frankfurt. So if you use your card in London, and after 2 hours you used it in, for example, in Frankfurt, so for a fact this could be a valid transaction, right? Because after all, we have time or time frame between 2 cities, and obviously if we refactor the plane time, so we can save, not for definite, but one element of it is like, if it is like over 2 hours, probably this is a valid transaction. Now, if we stay with it and we moved it from London to, for example, New York, and we still use the 2-hour time window here, so you definitely need to decline it, right? So whatever happened in transaction 1 here, and basically we have the 2 hours. So if it is like less than 2 hours, we probably need to decline it. So think about it as one element which you can use for your algorithm. Again, it's not as simple as you see it here, because after all, it's not one person who is traveling, right? It's not one flight. So what you need to factor in is how many flights. And last time I checked, I think it was like a few days or 2 weeks ago, it's roughly on average. So we're looking at the black line here. So we had roughly around 250K flights per week, which is like massive. And now you need also to multiply it with number of, passengers, how many people are traveling. So you end up with really big or large data set to handle. And remember, it's just part of the story, right? So because it's not full story to discuss how many flights and how many passengers, you still need to discuss how or to handle how many, for example, features you want to use from specific bank account or even from specific merchant, and you want to factor it all in your algorithm. Now, if we look at the architecture of this application, so what you see it here is, let's say that we're using some kind of banking application, whether it's your mobile app or, for example, you're using on the laptop or whatever. So we have it on one part here. So the solution will be deployed on the AWS, but it doesn't have to be. It could be deployed anywhere, just for the sake of simplicity here. So we have the gateway, API gateway, so this will handle all the requests for us. And then we have a service for validation. So validation also means different things for different people here. And this is where, you can use a cluster basically to handle it, right? So the cluster itself just refers to the platform, but the platform will allow you to scale up or down. So the Viridian solution essentially is a cloud-based solution, which means you don't need to spend your time, for example, on the configuration side of it. So you just need to connect it to the cloud, and this will handle it for you. Once you have it in the cluster, you can import your data. So you can import airports data, and you can import transactions data. So for the simplicity of this talk here, if you look at it, the airport data refers to a JSON file, but it could be anything, to be honest. It doesn't matter. So we have a code for it. So this is the airport code. We have description, and we have the GPS coordinates. So the GPS coordinates allow me to calculate time window between two airports. So how do we do it? Essentially, we take coordinates between two airports. So for example, London Stansted and Zurich, for example. And we add in, to the algorithm, basically the plane speed. And the plane speed, we can also take the average. And based on this average, we can say time window between two airports, factoring in the GBR coordinates or location for these two airports, as well as the speed of the plane will tell me basically this time window. Now, looking at the solution, I can use the IDE, but I think it's better if we can, look at it. So this is the code itself is available online, so you can try it out yourself. Essentially, what we're trying to do here is to connect to the Viridian. You don't need to, but obviously this will save you time. Or you can just download the platform as jar file and integrate it with your application. And we just enable this client, and we define also the statistic period on the cluster that we want. Obviously, when we start the client itself, we can start, importing the data. And the import is simply we're reading from the transaction as well as from the airport location. So the JSON file I showed you earlier, you can import it, and you can also use it to store a map. So you store transactions per user in the map. And the final part is to do this calculation. So we take two airports, we take the coordinates, we take the plane speed, and we simply check the validation. So this is, in simple terms, how you can achieve the fraud detection. But obviously, you can exchange this part here, right? Because if you remember from what I discussed earlier, you need to make sure to handle multiple algorithms at the same time. But obviously, this is, this part should be easy. What is important is to have this condition, because after all, you want to make sure, you can handle it. Now, sometimes you work with data scientists. So my background is a PhD in computer science, and data scientists in general don't talk programming languages. They prefer to use a simple interface, and simple interface for data scientists, after all, because fraud detection requires some kind of machine learning, and the machine learning requires to have some kind of Python, for example, or C++. So we have the SQL I mentioned earlier. So the SQL interface allows you to actually query your data to make sure that you have the right data in place. And the part where you connect it to AWS, so obviously you can sign up for a free tier on Amazon Web Services, and you define it here, you give it a name for it, and then you can use the JSON file to provide this part here. And this, once you load your data, so we have the airport data as well as transactions, you can do the calculation. And the matter of displaying, you can use, for example, create API, and this API will allow to connect any other microservices to your fraud detection algorithm. So hopefully this gives you the sense of what we're talking about, how you can implement the fraud detection. So this is first part, but second part of this demo is what is interesting in terms of doing the actual work, right? So in here you can see we have a, on one side we have transactions. So think about your bank transactions. So these transactions, in simple terms, you have date, for example, you have transaction, you have user, obviously you in this case, and you have a score. If you remember account score, so banks usually give a score for individuals. So whether based on your previous transactions or your credit score, I'm not sure if it is a term used here, but a credit score essentially is like a score to tell if this person, has some kind of credibility in terms of doing specific transactions or not. Another example is if you sign up to, for example, a new device, new mobile device or new laptop, and you try to connect to your bank account, you might get some kind of security check. You're logging in from a new IP address, so this will affect your score, obviously. And it requires to do these checks even if you use your card in different country. For example, in some banks you have to tell your bank essentially you're traveling to, I don't know, you're traveling to England, for example, so that they know and they add it to your score. So we're not interested in the score itself, because this is kind of like bank, from the bank side or from the finance side, and we just want to import this data into the platform. So based on this data, I want to define a trend. So I look at for example, in my case, I look at my previous transactions and I try to build a trend out of it. So this trend might go up or down. So for example, if I used my card with a different or wrong PIN number 3 times, for example, the bank might lock my card. So this means my trend will go down. If every time I use my card, I use the correct PIN, maybe my trend will stay flat or goes up. It depends and multiple factors. I will show you how we can do it. And once we define the trend, so based on the trend, I can predict if my next transaction will be valid or not, or whether it will be a fraud or not. So, and the output will be kind of like last column from last table, basically. So the algorithm will tell me whether it's a 0, we don't expect a fraud, or it's 1, so we might need to be cautious, or we might need to do extra check to check if what's going on. So the architecture for this solution here, so we have the real-time source. So this is your transactions coming into place. It could be Kafka, for example. And we take it to build two components. So we take it to build trend. First of all, this trend is just telling me how I'm doing over my transactions. And I group it by transactions. So these kind of like, based on the individuals. And I use this trend into feeding it to prediction. So after all, I end up with two maps. So one map will identify my trend, and the second map will identify whether there will be fraud or not. And then I can simply output it. So I can send it to File, for example. I can send it to Kafka, or in most cases, we can send it to microservice or web app, or even for SQL browser. So the part what we need is kind of like I mentioned simplicity in terms of defining it. So essentially, it's just 3 lines of code. Again, you just need to define pipeline and add this pipeline to your jet or to your platform. So the Hazelcast instance will actually, take it. So if you want to scale it, you just add more node to your application or to your solution. And we can have a score probability where we define the trend. So this will take the score, read it from your bank, add it to a map in order to define the trend. And the trend itself is simple transaction or simple equation based on how am I doing. So this can be used to calculate some kind of score and give me some kind of prediction if next transaction will be fraud or not. So my solution can detect the fraud transaction. So now we have the trend in first part, and this is where we can, use it to predict if the next transaction will be a fraud or not. And again, I mentioned the SQL. So the output, for example, for 30 minutes or for 30 transactions. So I can basically calculate it. So we have on one part transactions, and then we have time window. So time window doesn't matter much. It just tells me when is next transaction is expected. So obviously, for example, if I use my card, I don't know, 5 times a day, this is where it will detect this part here. So in the transaction number 8, I know first 4 future transaction will be normal, and the 5th will have some kind of fraud within the algorithm. Obviously, we're not interested in the actual machine learning solution, right? Because like I mentioned, you need some kind of combination between multiple sources or multiple algorithms in order to, get this score right. And obviously, it changes over time. So whatever we do it now might not be valid in next time window, maybe next hour or next application. So we always need to make sure we are able to take out part of the solution or algorithm and plug in a new way. And you want to do it in a way where you don't stop your application, right? Because, for example, some businesses require availability 24/7, for example, so you don't want to shut it even for a short period of time. So hopefully this gives you a sense for what can be done for fraud detection in terms of scaling, in terms of what challenges and solutions. And as I mentioned, we use the open source platform. So we have a large community here. So we're available on Slack. Our engineers are available on Slack. If you have any question in terms of how you want to use the platform, whether it's like fraud detection, or generally speaking, for real-time stream processing, or even for operation and data store. We do live streams on Twitch. We go through some kind of live coding on Twitch just to get you going. If you have any question, we do some kind of meetups, blogs, and everything related to communities. And with that being said, I think I'm left for 10 minutes for a question. So I think we're using Slido for questions. So I will just put it on the screen now. Say again? Okay. So with that being said, thanks for attending the talk and listening to this talk. So I'm open for questions. So let me just put it on the screen here. I need to. Now how to put this? Okay. So I have questions, but I don't know why it's not displaying on the screen. Okay. Okay, thank you. So we have a question here. Okay, so the first question is referring why I'm doing sleep 300 in the algorithm when we do the credit card score. So let me put it back again on the screen. So the question was why I'm doing this sleep in my code. Any idea? Sure. Yeah, that's right. But why I'm using it? The question is not if it matters or not. Why I'm using the 300 here? Yeah, that's the key word. If it is fast, so yeah, definitely it doesn't matter if it is test or not. Yeah. Yeah. Sure. Yeah. That's the keyword. So it happens really fast. So if you want to check it, right? So even if you want to give it to a data scientist, so remember that I'm not sure how many developers here and how many data scientists here or data engineers and so on. So generally speaking, we have multiple people who are working on, a solution. What you want is to, have some kind of mechanism within your code some way. So this is just allows us to, if you want to give this code to a data scientist to change this algorithm, for example, they should be able to see it in real time. So if I just remove it, they probably won't see the output, especially if you're using, logs from multiple sources and multiple libraries within your code. So the idea is just like to allow them basically to check the algorithm, how it's performing in real time. You can change it, you can lower it or increase it, doesn't matter much. But the idea of using it here is just because it happens so fast. Remember what we're talking about? We're talking about sub-milliseconds, and if you want to scale it as well. So you probably end up not being able to see it. So human eye not meant to read this one, but obviously because it's test, and data science involved, data engineers involved, so you want to have some kind of mechanism. So it doesn't matter much to the algorithm, to be honest. It's just like to give us a way of checking or tracking outcome or output in real time. Okay. So the question is, what algorithm have you tried to use in time series predictions, or are there? Okay, Thank you. So the question is, what algorithm have you tried to use in time series prediction, or are they not applicable in this data? I'm not sure if this question is exactly relevant to the demo or not, because I had 2 demos. Essentially, you can do it, time predictions, but like even myself, like I have PhD in computer science, and it's hard to get the right model. It's hard to get the yes, you can develop model with high accuracy in terms of the algorithm itself, whether it's like, you know, classification or clustering, and then, but it's not how it is when you deploy it, right? Because whatever you spent your time on when you develop your model doesn't reflect how well the model will perform when you put it in deployment or into production. So better to spend less time trying to figure out which algorithm to use, and you get a model right and deploy it, and once you have it right, you can use some kind of composite score where you can use multiple algorithms within your solution. Another part of it is to use some kind of AutoML. So AutoML, can help in here. So some machine learning platforms have some kind of AutoML. AutoML essentially answers your question. So instead of me or you trying to predict what kind of models you can use, you can deploy AutoML, and you can deploy it and change it from, based on the outcome. I think if you're interested in the previous question, we have a live stream. I think it's on Thursday, just how you can move from AutoML to real-time machine learning. So whoever asked this question, feel free to attend the Twitch. So we will discuss it in more detail this week. The other question is Hazelcast Jet for free no matter how many nodes I have in production? The answer is yes. I know some people or some companies use the open source version, and they use it for stream processing and over 200 nodes. There are some limitations in terms of the management center. So management center is part of it, which has some restrictions how many nodes you can have. So you can basically, it's kind of a report. But if you are a developer, you don't need it in terms of, but you can try it for 3 nodes, obviously. But when you scale it, the question for the Jet, yes, it's absolutely free. And yeah, you can scale it as many nodes as you want. So there is no limitations here. I'm not sure I understand this question. So maybe the person who asked just can. Well, this is like, it's more kind of like security question than performance. But I will answer it. So open source doesn't mean you can't use it. I know banks use open source. Obviously, they need some kind of protection, so they might not, claim which open source tools they use. But definitely, yes, it is possible. So I know also like some banks use the Hazelcast open source. So that's definitely yes. Hackers can exploit it. Well, first of all, we're talking about security, and yeah, if you're concerned about it, you probably need some kind of security layer on top of it. You can either implement it yourself or use some security features within Hazelcast. So it's your choice, but yes, it is possible. What was the last question? Sorry. Can you get it back? Yeah, I'm sorry. Yeah, I don't understand the second part of this question. Maybe you can explain who asked this. Yeah, I'm sorry. I don't. So have you occurred also issues with non-ACC? What is a non-ACC? What does it refer to? yeah. So come back. Maybe we can chat over coffee. Or with that being said, thanks very much for attending this talk. I hope you get something useful out of it. Things are changing in terms of how things are processed. So we're moving away from batch. So we're moving away from files and storage. What you want is to focus on real-time part of it. So even this, I'm not saying you have to use Hazelcast, but you really need to, if you want to, progress in your career, for example, you want to focus on the real-time side of it or real-time element of it, because most applications, use some kind of real-time implication. So if you look between, I don't know, 2000 to 210, or between 210 to 220, or between 220 to 223, things are dramatically increasing. So we're shifting away from batch, we're going to real time. So definitely it's one thing you can add it to your CV, the experience in real time stream processing. Yeah, I'll be available after this talk. If you have any question, feel free to ask, or if you have anything to chat about. Thanks very much. Thank you.